So today I'm going to talk about how we use Trino and Apache Pinot to do real-time analytics. So the brief intro for me, my name is Xiang, co-founder at Startree. So before that, I worked at Uber to build the streaming platform for data serving processing and analytics infrastructure. So from the open source side, I'm a PMC and a committer for Apache Pinot project. I'm also a contributor at Trino project. So Elon is working at right now it's a stealth mode startup. So he's a major guy who wrote the Trino Pinot connector, and before that he worked at Facebook's data infra team, price thing. So in today's agenda, so I'm going to first talk about how we do real-time analytics today, and what's being compromised for query flexibility and query latency. Then I will introduce Apache Pinot to solve the low latency part, and then Elon will talk about how we use Trino Pinot connector to cover the entire landscape for query flexibility as well as low query latency part. And then last part, we will show some benchmark and our future roadmaps. So let's first take a look at how we do data analysis today. Typically, we will have our raw data being hosted in the big data lake available for like all our users to process using like Spark, Hadoop, Trino, those kind of compute engine. And then we write some SQL to basically compute all our ETL jobs. So in this case, user have like the full flexibility to access all the data from the data lake and pick whatever they want, and they can apply whatever this kind of computations, and all those jobs is being like launched in an ad hoc manner and or like in a scheduled manner. So basically, users can do whatever they want. However, this job typically it takes like some time to retrieve all the results, as user need to read all the raw data from the data lake and then compute and launch those jobs. So let's take like one concrete example of like how we can do one, let's say, compute one business metrics for e-commerce business. Say we have a one-dimension table, which is called customer information. Let's say it's like 100K rows with a schema of like customer ID, name, gender, locations, and the factor table, which is user's order. Let's say it's a billion rows with a schema of order ID, date, customer ID, and those item informations. Now we want to generate some report or some sales numbers for how the number looks like for female customers in California. So from the raw data perspective, we need to write some SQL query to join two tables and then aggregate the results for that. So this query usually being split into like four phases if you think of how we really did the job, right? So the first one, we need to actually do the full table scan from the both table, right? So one full table scan on this table orders and another full table scan on the table customers. We will basically fetch all the records that's matched the given predicate, which is state equals California and the gender equals female. And the next phase we will do join. And this join phase will actually shuffle the data from both tables based on, let's say, the customer ID. And then the third phase we do group by, which will again shuffle the data based on the order date and the customer cities. Then we will do the real aggregation to sum all the order amount. Yeah, and then the reduce phase will actually collect all the group by results and render the final results to the end users. Then you will say, okay, for some cities, Los Angeles, you will get the total sales amount. So this data shuffle phase will contribute actually majorly to your query latency, including how to partition your data, how to serialize, and do network I/O and deserialize between your sending data from each phase to each phase. So here we'll get flexibility to do any kind of computation. However, we pay high cost on the disk network I/O and this data partitioning and the data CG. So To optimize this query performance, then the ETL comes, right? So ETL in ETL job, user can actually pre-join this factor table and this dimension table, and then we can query on this pre-joined table. So in the previous example, we can actually pre-join the customer table and the order table to a new table. Let's say call it user order join table, which will be translated into like another billion row with full joined schema, right? So in this case, we can actually compute the metrics based on the order amount, and then we can do slicing and dicing on top of this user dimension like genders or locations and the time or whatever. So say if we want to see the average amount of the order per month for a male customer in Los Angeles or female engineer in every city, then you can actually quickly just do a filter and then do a group by, then do the aggregation. Then you can just get the results. So in this case, the downside of like the pre-joined table is that the query time is kind of still proportional to the total number of the rows you have to scan, right? So in the above example, there are like a million rows that match the predicate of, let's say, state California and the gender female. Then this 1 million rows will be computed or aggregated on the fly in order to render the final results. So a noticeable improvement from this above, from the previous approach is to let's do pre-aggregation. So pre-aggregation is something we can do once we know that this is the number we really want. So we can pre-aggregate and generate the final results we want. And then during the query time, we will already know the results and we can just query it. So for example, in this case, we will generate this aggregated table. Let's say we do date, gender, location, and those sum of the amount and the sum of the sold items. We can do pre-aggregation on those numbers. And assuming we have 1 million unique combinations of this date, gender, and the location per month, then the total number of the records after the pre-aggregation can be reduced to, let's say, 12 million for 1 year worth of the data. Think of like you have 1 million customers and you have 12 months, right? So these 12 million rows are the data size you want to do the aggregation based on this pre-aggregated table. So in this case, we pre-aggregate all the data based on those dimensions, and then we can rewrite this query to something like here. Basically, we just filter on the state and the gender, and then we can group by the months of the data and the city, and then we will get what we want. So in this query, we furthermore reduced the query runtime workload. However, my query time is still like kind of proportional to the multiplication of the non-group by the columns. Saying it's like my dimension combinations found out will still be the major fact which will drive the query performance. So yeah, so in this case, another thing comes called cubing. So this is like the most familiar solution for like OLAP users. Basically, cubing is a solution to achieve like a constant query latency, which users can actually pre-compute all the metrics they are interested and based on all the dimension combinations they want. So for any query comes in, it will always be an exact 1 row match in order to answer this question. So for example, now we can say we have a fully cubed table, and then we will just say we want to select the sum amount and the month and the city based on a given criteria. So we will basically change the query into this where my data equals none kind of thing. So the downside of the pre-cubing solution is that my data size is actually the multiplication of the dimension cardinality. So if we add a new dimension into my table, then based on like the cardinality of the new dimension, the whole data size will actually be exponential growth based on the cardinality of the new columns. So this approach will kind of not being scaled by the organic growth of the user's data size, as well as the total number of the dimensions growth once the business requirements are more coming in. So let's just like from a very high view of like take a step back, and the first graph that we want to show. So Trino is actually a perfect engine to do all this ad hoc manner, right? So in terms of the computations, you can use Trino to write a full SQL to do all the drawings. And if you are looking for something like doing pre-joins and pre-aggregations and then pre-cubings, so Pinot will be like one solution for that. So on the very high level of Pinot, so it's basically an OLAP data store. So built from LinkedIn, and right now it's being widely adopted for like many user-facing applications, business analytics use cases, and we also use it for like anomaly detection use cases as well. So when we say like low latency, it's actually been including like two parts. So one is about the low data ingestion latency. The other part is about the low query latency. So this means Pinot will directly consume data from like the real-time data sources like Kafka, Amazon Kinesis, or like Apache Parser. So all those real-time data sets, data sources will be available. So apart from like these real-time data sources, user can also load data using Hadoop, Spark, from like blob stores like S3 or Google Cloud Storage and Azure Data Lake. So in our production environment, handles a workload of like ingesting millions of events per second and serving like thousands of queries per second with like milliseconds latency. So our largest deployment in LinkedIn is about like 1,000 node with like 1 or 2 SRE to operate. And recently, Stripe also launched their biggest table. It's like one table is probably around 100 terabytes with like 100,000, 100 kind of VMs in order to serve like one table for their use cases. Now let's try to expand this Pinot box. So Pinot itself has like three major components. So it's a controller, zookeeper, and broker and the servers. So all the data are actually being stored in Pinot servers. So Pinot controller will be responsible for all the cluster and the data management and all the metadata. And all the queries are going to those Pinot brokers, which will maintain all the routing tables and also pick the best strategy in order to send all your scattered queries from the selected Pinot servers. So the secrets behind the Pinot to optimize all the query performance across all the layers, where it's basically from all the storage to the query part. So from the storage layer, Pinot implements its own columnar format, along with like compression, and we do byte encoding, and we also do like bit and run length encoding once we are seeing like there's storage pressure there. And from this query processing layer, Pinot has implemented multiple index technologies like inverting index, Bloom filter, sorting index, starter index to speed up queries. So from the aggregation perspective, Pinot also leverages starter index to pre-aggregate data in a more cost-efficient manner. So starter is actually one unique technology. We're providing the way to do partial pre-aggregation. And for example, we just pre-aggregate those metrics that contains more than a threshold of, let's say, 1,000 orders in like all dimension combinations, which means we only index those, or we only pre-compute those important or significant dimension combinations, which means comparing to like the pre-cubing solution, which everything will be answered in like 01 time. Here, you can think of everything will be answered in like in like 100 time, which means Pinot won't scan more than 100 records in order to answer your question. So this is like one of the perfect way of trade-off between the latency and the space by like partially doing those pre-aggregation technologies. So that we can actually be helping to do the hard upper bound for any kind of the queries. That's also why we can help users to do user-facing analytics. Okay, cool. Next, let me hand off to Ilan to introduce the Trino Pinot connectors.
Xiangfu gave a great overview of Pinot. This is a short overview of Trino. I'm sure you're all very familiar with it. The client submits a query. It goes to the coordinator where it's parsed and analyzed. Then there's a plan, there's logical plan, distributed plan, and then it's scheduled on the workers, and then the results are sent back to the client. And then this is how we connect Trino to Pinot, where Pinot can connect to different like BI visualization tools. So can Trino as well, including ad hoc analysis, and you could do more complex joins and filtered aggregations, window functions with Pinot data, including like all the benefits that Xiangfu mentioned with the star tree and inverted indexes and range indexes and everything. So just this is a workflow of an example query where you have a join between two Pinot tables, and you can see that the top one, the engine decided to route it to the Pinot broker, which will fan out and gather the results and then reduce them because there's an aggregation. The second table actually goes directly to the servers because there's no aggregation there, and then you can join them in Trino, which gives you the power to do a lot more complex analysis. And I'll explain the different types of queries, the broker and server query. So the first advantage of a broker query is that we can do pushdown. So aggregation pushdown could make the difference between milliseconds and minutes, including Pinot servers crashing due to selecting all the rows and then transporting them to Trino, where instead you can just use the star tree indexes, for example, to get the pre-aggregated values, similar to what Xiangfu mentioned. So if aggregation pushdown is enabled, then it will actually construct a broker query with the group by columns. We can now do distinct columns with the Pinot 8 connector and complex group by expressions, which I'll explain in a upcoming slide. So the newest features are that we can do complex group by and order by expressions and use the native Pinot libraries to parse and find the return types of the values. And quotes are now supported. Yuya Ebihara, I hope I'm pronouncing his name right, just implemented that, and now I updated it to work with Pinot 8 everywhere in the query. And you can also, if you notice now, we also support numbered fields in the group by and order by, and soon we'll have having support. We actually have a working POC, and we use it where I work. I'll be open sourcing it very soon. We just want a few pull requests to land, and then I'll rebase them. I'll go over that at the end too. So now you can also order by, which if you'll notice here, this query is in quotes, which we call it a pass-through query. So it will effectively be like you're submitting a Pinot query through Trino, and then you push down and aggregations, filters, and limit into the Pinot query. So it'll modify the broker request. Here's another example of a workflow. So if you have this same query with the two joins, what it'll do is it will go to the server, but instead of using the server client that we had in Pinot 6, I was able to work with Pinot folks to contribute a gRPC endpoint and then also implement it in the Trino connector so that we don't have that issue where you select a large amount of data and then it crashes. And in tests, it's actually faster than the previous server connector. And you can do a lot of powerful things there. Like you can use MaxBy and filtered aggregations in Trino that you couldn't do in Pinot yet. And also you can do joins and other things like that. And you never have to worry about the Pinot servers crashing because they won't buffer the results in memory. They'll just stream them to the Trino workers. So this really opened up a lot of opportunities. This can also be used to migrate Pinot clusters or copy Pinot tables easily, just using SQL. So there's also a lot of ongoing and future work that we're doing. We implemented insert, which I just wanted to give a brief low-level explanation. So what we do is we replace the offline segments with the new segments and delete any extra offline segments. The insert is now fully disk-based. It uses the Pinot libraries for like generic file writer and segment mapper, and then ships the segment to Pinot workers. So you can actually have a large amount of these running in parallel, and they won't use up memory. We have a local SSD that we use to write the temporary data, and the bucket function ensures that if you have a time column, all the rows from that would go into one segment go to one worker. And this way and then it chunks it into evenly sized segments, which is configurable in the Pinot config. So what that does is it allows Pinot, if it has evenly sized segments, then you can parallelize better. It also has less load on the Pinot controller when you're uploading the segments. And we use this is heavily relied upon where we work, and I'll be updating the pull request for it. It's going to be rebased off of the Pinot 8 pull request. And there's two modes, one where you insert and add new segments, and another where you, it's kind of like an upsert, but it's more like you just insert, replace in MySQL, similar to that, where it just replaces segments with the same day or hour, depending on what push frequency you had defined in your table config. And then some other ongoing work, table creation and segment deletion. So in upcoming pull requests, we expose the segment column and other virtual columns. The segment column can be used similar to a Hive partition key, where it can just delete the entire segment by mentioning the segment name in the filter. It can also do pruning based on the segment name. And then we also implemented create table, alter table, drop column, where you can actually pass the JSON that you would give to the Pinot like UI, the Swagger UI, and it'll create the table for you. And you can update the table configs, and it's pretty powerful. So you can actually do show create table, and it'll show the create statements, and then you can cut and paste that to copy it, table definition, for example. And it's kind of upgrade proof because you're just passing it JSON, which may change from release to release in Pinot as they add more config options like primary key columns and dimension table support. Let's see what else. So we did a benchmark on a small like set of servers just to show the difference between aggregation pushdown enabled and disabled. Now the servers were small, but we were able to show that if you select, for example, if you select count, it'll be a pretty much linear time increase, but with aggregation pushdown, it turns it into a broker query. And you can see just a very tiny increase in the amount of time because it's just reading from more segments to get the star tree information for the aggregates. And this can also make the difference between crashing a Pinot server and queries taking minutes versus queries taking milliseconds and leveraging the broker. And thank you for watching. And I want to thank everyone at Starburst and Startree for all the help and advice and helping make this connector great. And learning's been great. and always reach out to me in Slack. You can ask any questions.